important. I want to do two different things today. So hopefully we will do one before the break, the second one after the break. The first thing I'm going to do is to do a more elaborate explanation of why we use IQ sampling or complex sampling in digital signal processing. I wanted to get into the details of it because on the previous week I mentioned some things about Fourier transforms and negative frequencies, but I think it is worth to do some examples to actually see what happens when we introduce complex numbers and we play with the Fourier transform and with frequency translations. So that would be the first part of today. And the second part, which should hopefully be after the break, will be about spectral analysis. So that means we have some signals, we compute a spectrum, and then in the spectrum, we hopefully should be able to detect the signals if they have enough signal to noise ratio. And for that, I will show you how to generate some simple types of signals in GNU radio, such as narrowband signals or CW carriers, basically a tone, a constant tone of constant frequency and amplitude, and also wideband signals. So that is a signal which has some particular bandwidth to it and occupies some portion of the spectrum. So let's get started. I have all the flow graphs already in the GitHub repository. The first one, I think I'm going to try to replicate it in real time. The second one, maybe I will just open a copy. So I'm going to use 100 kilo samples per second. The sample rate is not very important because this is some kind of simulation or demonstration. I'm going to call this IQ sampling 2 because I have an IQ sampling 1 already. And the first thing I'm going to do is something very, very simple. I'm going to use real sampling, so real signals, real valued signals. And I'm going to show you how a cosine signal looks like. So I'm pulling in a signal source. This is cosine, so that is fine. And then I want to change the data type to floating point. And I want to be able to set the frequency. So for that, we know there is something called a Qt GUI entry. And I'm going to call this frequency. I can put a label, which is the frequency in hertz. It's going to be a float. And maybe I'm going to put this as 10 kilohertz. I don't know if that's fine, or maybe 1 kilohertz. So the next thing I need to do is, because this is a simulation, I need a throttle block which sets the data rate or the speed at which the simulation runs. This is mostly to avoid using 100% of the CPU. And I'm going to keep the parameters as default. So sample rate, 100 kilosamples per second. And I want to show this both in time and frequency. So this is quite similar to the last flow graph I was doing last week about audio signals. I'm using the time sync and the frequency sync. Where is it here? I need to change the data type on these two to floating point. The number of points, to keep the math simple, I'm going to set 1,000 samples. So that is 10 milliseconds because I have 100,000 samples per second. And then on the frequency sync, I'm going to use 4,096 points, which, as I mentioned last week, is my favorite FFT size for this block. It's the most useful one, I think, as a default. And that's about it. So this should be not surprising at all when I run the flow graph. What I have is a cosine function, and you can see it here. It has a frequency of 1 kilohertz. So that means that in 10 milliseconds, my x-axis is 10 milliseconds. I should have 10 cycles. And I'm not even going to count them. I think there are 10 cycles. And in the frequency domain, what we have is at 1 kilohertz, we have a spike. So that means, yeah, there is a tone at 1 kilohertz. But as I mentioned last week, we also get a tone at -1 kilohertz. And there are many reasons for this or many explanations one could give. The most straightforward explanation and mathematically true explanation is you have this cosine function, you compute the Fourier transform, and this is what you get. You get two Dirac deltas at plus the frequency and minus the frequency. And that is true, but it is somewhat unsatisfying, at least for me. So something else that can be said is this is a real valued signal. So when you have a real valued signal, the Fourier transform is symmetric. You get exactly the same on the negative frequencies and on the positive frequencies. And we see that is true here. We also get some minor spikes here, and those are just because of numerical errors. So when the computer is calculating this sine wave, it's not going to be perfectly exact, and we can see that on the FFT. So that's another explanation, properties of the Fourier transform. But the most intuitive explanation I want to give is that it's what I mentioned last week. The frequency is the inverse of the period. The period is the distance between two peaks. So for example, the distance here, which we can read from the flow graph, it's 1 millisecond. And it's supposed to be a positive number. So because it's a time duration, it is a period. So the frequency is supposed to be a positive number. And then we get a positive frequency, but since formally the Fourier transform has negative and positive frequencies as the output, we also get the same thing in a negative frequency. Somehow, you can also think someone could say the period here is -1 millisecond if they counted from here to there. It's like going 1 millisecond backwards in time. And that might also be a sensible way to put it. I think no surprises so far. Any questions about this? Okay, the next thing I'm going to show is how to move things in frequency, because you can imagine that is an important operation. We are always thinking about time and frequency when we do signal analysis, and we want to select things in time. There might be a time interval which is of interest to us because that is when an event happens. And selecting things in time or moving things in time is very easy. We just have the stream of IQ samples in time and we select what is the time interval we are interested in. It's basically selecting some samples in the file or selecting some bytes in the file. It's just as simple as that. But operating with frequency is somewhat more complicated. We need to do some calculations. If we want to do a selection of a frequency range, or if we want to move things in frequency, for example, I could say, I'm interested in this signal, which is currently at 1 kilohertz, but I want to shift everything in frequency so that this is now at 0 kilohertz, because that is where the center is for me. And it is actually easier for me to do operations of signals that are in the center that are 0 kilohertz. So I want to shift things to move this signal to the center. And how we could do that, I'm going to show you a way. So we are going to use the properties of trigonometric functions. I'm going to add a new cosine signal, and I'm going to copy and paste, and I'm going to give it a different frequency. And for reasons that I will explain, I'm going to call this local oscillator frequency because traditionally, when this is used in a radio receiver or radio transmitter, it is called local oscillator. It is a frequency that we use to perform a frequency shift of something because we are either receiving things at a certain frequency, but we want to move them at a lower frequency in which they are more easy to process, or the other way around. Maybe we have a transmitter, we are generating signals at a low frequency because it is easier, and then we want to shift them up to anywhere. It might be gigahertz of frequency at the final frequency where they need to be transmitted. And the thing which is used electronically in hardware to accomplish that is called the local oscillator. And the same name is also maintained in digital signal processing because we do the same operation just mathematically in the computer. So signal source, and the thing I'm going to do is to multiply the two signals together, and you will see what that accomplishes in a second. So let me change the frequency. I need to put here LO frequency. And I should also remember to set this as the variable frequency because otherwise it will not track the value I set here. And I want to add a second input to this one and a second input to this one as well to show you what's the result of the multiplication. And we could look at some formulas, but we can also do it experimentally in this way. So at the moment, what's happening with my second signal? Something is not right because I think I have set it to 0 Hertz, which should be a constant, basically something which is 1 all the time, but I'm still seeing a 1 kHz signal. So I think I've forgotten to set something. Okay, yeah, I see what I wanted to do is to show you three different signals. I want to show you the product of the signals, but I want to show you also each of the signals individually. That is what was missing. And maybe I can add labels to this one. So the labels are on configuration. So you can see there is signal 1, signal 2, signal 3. We can change them. I'm going to say input signal, local oscillator, and then product. Sorry, that should be known. And then signal 3 should be product. And in that way, it should be easier for us to identify which is which. So this is input signal, local oscillator, and then product. And now it should be fine. Okay. So I'm going to disable the product by now. It's the green one. By clicking, we can enable and disable. We have the original 1 kHz input signal in blue. We have the local oscillator in red. And things look like what we would expect, except in here in the frequency domain, there is something wrong. Let me look back. Yes, I have an error here. I have connected the product, but I want the original signal. So let me do this again. Okay. So now we see the local oscillator is a constant, and a constant is something which is at 0 Hertz on the frequency domain. It doesn't change. So there we have the local oscillator. At this moment, it is not very interesting what happens with the product, because if I multiply anything with 1, the result is just the same as the original input. But let me show you what happens, for example, if I multiply with 100 Hertz of local oscillator, and it takes a little bit of time to update. So what happens is, this is the 100 Hertz local oscillator in red. I have one cycle in 10 milliseconds. This is the input signal, which is the same as before. And then the product, you can sort of see that it makes sense in the time domain. So when this is positive and large, the product is basically the same as the input signal. But then this one decreases, so the product also decreases. There is a zero crossing. So the product now has the opposite sign to the input signal. Now this is negative and large. So this is what we get here. And so it keeps repeating. So that is one way we could reason about the product. It is basically what you get by multiplying these two signals together. But we can do other kinds of analysis. So for example, if we go to the frequency domain for the local oscillator, we see something at plus 10 kilohertz, plus 100 hertz and minus 100 hertz. And now for the product, we see several things. We see 1.1 kilohertz, 0.9 kilohertz, which is the same. So these two peaks are the same as 1 kilohertz plus 100 hertz, 1 kilohertz minus 100 hertz. And then in the negative portion of the spectrum, I have the same, just because real signals, it is always going to be symmetric. So maybe some of you remember some trigonometric formulas about what happens when we multiply trigonometric functions. For example, what happens when we multiply two cosines of different frequencies. And there's a formula for that. It can be written as the sum of two different trigonometric functions with different frequencies. And the frequencies we get are the sum of the two input frequencies and the difference of those frequencies. So that is the reason we see these two signals here. Mathematically, the multiplication of two cosines is the addition of frequencies and the subtraction of frequencies. And we can try to make some use of this by, for example, if I want to translate this thing in frequency to make it come to 0, I have already shifted it by 100 hertz. So I need to shift it by 900 hertz more. And that is basically the same thing as setting this to be the same frequency. So by doing that, we get on the product the difference of frequencies, which is a constant. It is something at 0 hertz, but we also get the sum of frequencies. So this is a term we do not actually want. We could use a filter to remove it, but nevertheless, it is there because when we multiply trigonometric functions, we get the sum and difference of frequencies. So it's not really a frequency translation. It is something similar, but we get additional signals we don't want. Any questions at this point?
I guess just a comment again to sort of bring this into like everyday life experience. If you think of sort of two signals that beat together, you might be familiar with sort of sound frequencies that are slightly different, and then you hear this sort of wow, 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 which is the the envelope of the mixing of those, which essentially is the same phenomenon. Or the other sort of everyday example, which I think Daniel mentioned last week, is tuning a car radio where you're changing the local oscillator frequency, which is then matching the frequency of the FM station that you want to listen to, and then moving that down to a frequency that it gets sampled at and sent to the amplifier and the speakers.
Yeah, the examples about two signals which are slightly of a different frequency, that is a good one. We can simulate it here, for example, by setting a difference of 1 hertz. And you can see there is this whoa, whoa, whoa effect, which is basically a 1 hertz tone that we can see here not very well because of the FFT resolution. And that comes up in music all the time when you have two instruments which are slightly out of pitch. You can hear this beat frequency, which is how it's called. Okay, so what I want to do now is I'm going to do the same thing, but with complex functions, because maybe we accomplish something by going to complex numbers. Since the thing we wanted to do here was a frequency translation, and we get it, but we also get this high frequency term we do not really want. So does complex numbers, do complex numbers help us in any way? And we will see that they actually help us. So the way I'm going to frame this is very simple. I'm going to copy and paste all of this. I'm going to disable this one, and I'm going to change the data type of all of these blocks to complex at the same time, just by selecting all of them and pressing the up arrow key on my keyboard. That changes the data types of all the selected blocks. So now everything is complex. I recall that the orange color here means real data type or floating point data type. The blue color means complex data type, which will be the most common data type for us in all the remaining tutorials. So I think I'm going to just go ahead and play this. I will disable my, oh, I need to change the labels because now I have a real part, imaginary part, etc., etc. So these labels are no longer true. So I'm going to say real part, input signal, imaginary part, the product. So this should be local oscillator, real part. The signal 4 should be local oscillator, imaginary part. Signal 5 should be the product, real part. And signal 6 should be the product, imaginary part. And on the FFT display, I do not have to change anything because the complex signal is used as a whole, and the FFT is computed, and we only represent the power of the FFT, which is the modulus or absolute value of the complex numbers which come out. But in the time domain, we have the real and imaginary parts separately. So I'm going to disable things to explain them step by step. So the first thing I should say is what is this complex cosine? So this is not really a cosine function. This is a complex exponential of frequency 1 kilohertz. If you have treated with complex exponentials or phasors or polar representation of a complex number before, you sort of know the kind of thing I'm referring to is this exponential of 2 pi I or 2 pi j times the frequency times time. So that is the thing we have in here, and there is Euler's formula, which says that that exponential is the same thing as the cosine function of the frequency multiplied by time plus I or plus j, the sine function of the frequency multiplied by time. So basically, one of these complex cosine functions, as GNU Radio calls them, is the cosine on the real part, which we can see here in blue, and the sine function of the same frequency, which we can see here in red. And that is what we have, basically. Cosine and sine of the same function, red and blue. But now what we can do is to do a negative frequency. And I'm realizing I didn't do that before with real signals. So I'm going to go back and do that, because I want to convince you that for real signals, positive frequencies and negative frequencies are exactly the same. So what I'm going to do is I'm going to put minus 1000 hertz in here. It's just the same frequency, opposite sign. I click and we can see this, the phase has changed. So the position of this is no longer the same, but that has to do with the moment I have pressed the enter on my keyboard to apply this frequency change, because the frequency change is applied instantaneously. And so what we get depends on when I have exactly hit enter. There is basically no other alignment between this time representation and the signal here. So minus 1000 hertz, it looks the same. The distance between peaks is 1000 1 millisecond, sorry. So you can see it's basically just the same. And every time I change sign, I get it in a different position because of this thing about how frequency updating works, but it is the same shape for the cosine function. And you can see on the FFT, it's the same. There is actually no difference. So now my question is, if we do the same thing with complex numbers, will there be any difference? And let's see. Maybe you already know the answer, but what I want you to notice is the relative position of these two. We have blue and then red. And if I put minus 1000, we have red and then blue. So now we have something which is different, because we have the real part and we have the imaginary part. So each of them individually, if I only look at the blue signal, it is the same as before. It is 1 kilohertz. I cannot tell whether it is plus 1 kilohertz or minus 1 kilohertz. But if I look at the combined effect of the two of them, I can decide whether I'm looking at a positive frequency or a negative frequency by looking at whether the real part comes before the imaginary part or afterwards. So for positive frequencies, we see that the peaks on the real part come before the peaks on the imaginary part. And there's a way of remembering this, which is I leads Q. Usually the real part is called I for in phase, and the imaginary part is called Q for quadrature. basically because of reasons that you have a local oscillator and what you get in the real part is what's in phase with your local oscillator, and what you get on the imaginary part is what is 90 degrees out of phase with the local oscillator, and 90 degrees is the same as saying quadrature. So if you see I and Q, or IQ, that's the same as real and imaginary. So I leads Q, that's the way of remembering. When the frequency is positive, I leads Q. When the frequency is negative, it's the other way around, Q leads I. And we can see the change also in the FT. I'm going to zoom in so that the difference is easier to see. This is minus 1 kilohertz. It's on the negative part of the spectrum. This is plus 1 kilohertz. And mathematically, the FFT is able to know the difference between these two cases because there is an imaginary part. And that is what also causes there to be just a single thing on the FFT. Before, with only the real part, we had plus and minus 1 kilohertz. Now we only have either plus or minus. And this is because for complex signals, it makes complete sense to speak about positive and negative frequencies as different things which are tangible because of this I leads Q versus Q leads I thing. And so the FFT can discern between negative and positive frequencies. It is able to show us just the positive frequency when we give them such a complex cosine function of 1 kilohertz. Everything clear so far? Okay.
Any questions?
Any questions? Okay, good. So what happens with the local oscillator? Basically the same. It is now 1, and I can show it as the, sorry, not the product, the local oscillator. So the same thing as before, because I haven't changed its frequency so far. And the product, we can see that it is still the same as the original input signal. The spectrum, it is plus 1 kilohertz. But let's see what happens when I put 100 hertz, which is the same thing I did before. When I do this, maybe I have many different things. So let me go step by step. So on the local oscillator, which is the green and black, I have this 100 hertz, and you can see I, which is the green, leads Q because it's positive. On the product, which is the cyan and magenta, it's kind of harder to see what happens with the multiplication, because now we are doing the multiplication of complex numbers, and there is a formula for that. But if you were to do it on paper, you should be able to check that we get these these cyan and magenta things, which again, cyan leads magenta, as you can see here, because we get a positive frequency. Maybe it's easier to figure out what is happening on the FFT. So we have the 1 kilohertz input signal, we have the 100 hertz input signal, and the result is a single signal, which is 1.1 kilohertz. So we have only the sum of frequencies in this case. And there is a mathematical reason for that, because we have exponentials. So think of them as exponential functions. They have the frequency and the time on the exponent. If we multiply two exponential functions, that is equivalent to adding the exponents. So since we add the exponents, we add the frequencies. Those are the things which are on the exponent. So that is the formula. That is the mathematical explanation for why when we multiply these complex cosines or these complex exponentials, we get only the sum of frequencies. And that is very useful, because if I want this green thing, which is the product, to appear at DC at 0 hertz, the thing I need to set my local oscillator frequency is basically the opposite from this one, so minus 1000 hertz. And now we can see the product is a constant. It's not one, so it has some phase. It has basically non-zero imaginary and real part, but it is a constant. We have obtained something which is on the DC component on zero. And actually the value here, so the complex number, the constant complex number we get, its phase tells us about the phase difference of the input signal and the local oscillator. So you could read out the phase difference in here, basically the time difference between these blue and these green signals. And that is manifested as something like the arc tangent of the imaginary divided by the real, basically the phase of the complex number. So that is very useful. Now you know how to measure phase of something with respect to a reference signal of either the same frequency or an opposite frequency. So that is something else I should mention. To keep things simple, I'm multiplying complex numbers. So I have a multiplication here. What happens is the frequencies add together, but usually in many practical applications, it is easier to think about setting the local oscillator to the same frequency we want to receive. And the example Steve gave about the radio on a car is a very good one here. So if we want to tune to some particular station and we know the frequency, maybe it's I don't know, 95 megahertz. It is easier to think that we need to generate the local oscillator at 95 megahertz rather than to think, oh, we need to change the sign, so it needs to be minus 95 megahertz. And the way we deal with that, or the way we adjust for that, is to perform a multiply conjugate. So multiply conjugate is the same as multiply, but perform a complex conjugate of the second term. So I'm going to show exactly what the operation is. Sorry. So multiply conjugate would be like this, and this is equivalent to multiply and put a complex conjugate on one of the inputs. So either way you do it, it's easier to do it with a multiply conjugate. You are taking the frequency of this one, taking the frequency of this one, but with the minus sign, because the effect of the complex conjugate is to flip everything in frequency. So it inverts the sign of the frequencies. And so you do not need to remember that you need to use a minus sign in here. That's the way that it's normally done in practice. But for today, I'm not going to use complex conjugate. I'm going to use the product. So we can remember that frequencies add. And if we want to shift something to the left, we need a negative frequency here. Uh, any questions? Okay. So to summarize, what happens with complex signals is that first of all, we are able to distinguish between positive and negative frequencies because we can compare the imaginary part and the real part and look at which of them is leading, which of them has peaks coming before the other one. Complex signals are more easier to work with for many useful simple operations, such as frequency translation. For frequency translation, we can multiply any signal. I'm using here a cosine function for the sake of the example, but this could be anything. This could be a very complicated signal we have recorded with a radio receiver. It might be multiple FM radio stations. It might be anything. In here, we use a cosine function to shift it in frequency. So it will shift anything in frequency. Here, I'm just using a single simple signal, but anything we put in here will be shifted in frequency. So that's a simple and useful operation. It makes sense for us to use complex signals just for the sake of having access to this useful operation in such a simple way. With real signals, it is more difficult because we have the additional sum of frequencies term, which would appear here at 2 kilohertz, and we need to filter it out or something like that. So those are the main reasons. And there is also that the Fourier transform ultimately it's a complex mathematical thing. In the definition, it has complex numbers. There is no way to have it without complex numbers. And that's the reason why we always have positive and negative frequencies, even with real input signals. What happens with real input signals is we have the same thing on the right and left halves of the spectrum. There is another thing I wanted to show about complex signals to help intuition. And for that, I'm going to use a new block, which is the constellation sync. So I'm going to put it here and to show you how it looks like, and I'm going to explain what it does. So what this thing does, I've only connected it to the input signal, and what this does is it plots on the complex plane. So you have in phase, this is the real part, and quadrature, this is the imaginary part. So it plots all these points. It has a number of points that it plots. By default, it's 1024. I could change it. So basically all the points here, which I can, by the way, you can access settings on these plots either by clicking the middle mouse button if you have it on your mouse, and then you have a menu. I think right click is, yeah, right click doesn't work. So middle mouse button, and then you select whatever you want to change. And the thing I wanted to change here is to add markers. So you can add, but for the input signal, you can add, so a circle here, and for the imaginary part, a marker, a circle as well. So the samples we have, remember that this is discrete time, so we don't really have a continuous signal in the computer. We have this sample, the next sample, etc., etc. They are those that are marked with dots. And if we represent all of them in the complex plane, regardless of time, this is what we get. Basically, this is something that is going around in a circle. It is not easy to see that it's going around because we are representing 10 rotations, more or less, in the same plot, but I will reduce the frequency so that you can see it. What else do I want to mention about this? Oh, yeah. So if you don't have a middle mouse button, but still you want to access these settings, there is another way. We can go back to the Qt GUI time sync, and there is somewhere in config where it says control panel, and you can say yes. And if you do that, then you get many of those settings here. Maybe not all of them. So yeah, but at least you get some additional settings here that you can use. I don't know if right clicking, no, that doesn't seem to work. So anyhow, since I'm saying that this should be a circle, but it doesn't look like a circle because the size of this is a rectangle, I also want to show you how to arrange these plots in a nicer way so that this is actually closer to a square, and then we get a real circle in here. So let me disable the control panel because we don't need it. And there is a GUI hint in here. This is used to arrange plots in the GUI. And there's documentation in the wiki about how to set this up. But in the most simple cases, it is just coordinates on a grid. So think about coordinates for a matrix or something like that. If we want to put this in the first row, first column, it should be 0, 0. Everything is numbered beginning at 0. So 0, 0, first row, first column. And I want to put the constellation sync in the first row, second column, so 0, 1. And then this one, maybe I want to put it on the first row, second row, so below the other two plots, first column, so that is 1, 0. And then if I click play, we can see things are as we wanted them to be. So the time sync here, first row, first column, constellation, first row, second column, and this one, second row, first column. This is not exactly a square, but it's less rectangular than before, so we can see that this is a circle. And what I want to do now is to set a very low frequency, maybe 0.1 hertz, and you can see that the thing is rotating, and it is rotating counterclockwise. So when we look at positive functions on the positive frequencies, sorry, on the complex plane, they rotate in a counterclockwise direction. If I change the negative frequency, then we see that it begins to rotate clockwise. So if we look at the complex signal as a whole, we can plot it on the complex plane and figure out whether the frequency is positive or negative by looking at whether it is rotating clockwise or counterclockwise. Because we have two dimensions, it makes sense to speak about, hey, this thing is rotating clockwise or this thing is rotating counterclockwise. Think of a wheel. I was mentioning the example of a wheel the other time. We can paint a white point on the rim of the wheel, maybe to make it more clear, and we rotate it. We have two possible directions, so it makes sense to have a sign together with the frequency that it says what's the direction of rotation. To make this even more clear, what I'm going to do is to add to this one the real part and the imaginary part. So that is also another useful thing for you to learn. There are some type converter blocks. So when you want to convert from complex to real, or actually complex to float, this one will give you access to the real and imaginary parts by separate. You can see the first output port is called re for real part. The second is called im for imaginary part. And what I want to do is basically connect. I want three inputs. I want to connect these like so, but that is illegal because I cannot mix data types. So what I want to do is to convert each of these to a complex number by putting 0 in the other part. So let me make this more clear by putting float to complex, float to complex. I'm going to connect them like this. So the real part will go to the real part, and we will put zeros in the imaginary part. The imaginary part will go to the imaginary part of these different input, and we are going to put zeros in the real part. So that is the way of plotting just the real part, just the imaginary part. And then what I want to do is to put zeros. So this is another block for you to learn. There is something called null source. When you want to generate zeros, you can use a null source, which generates zeros. Null is basically another name for zero in this context. And another way you can generate zeros is there is a constant source, and you can set the constant. So we can say this is floating point and this is 0. So any of these two ways is a good way to generate zeros. And of course, I cannot connect the same. Yeah, I wanted to connect it like this. I cannot connect the two of them at the same time. You cannot connect two outputs to the same input. So I'm going to remove this. And basically, the plot looks like what you could imagine. This is the complex number, which is going around the circle. This is the real part. It is basically the projection of this on the real axis. I can even, there is a grid somewhere, so you can see the real axis projection is the red thing, and the imaginary part is the green thing, which is going up and down. But what I want you to see is what happens if I do 0.1 hertz. So the complex number is rotating counterclockwise because the frequency is positive. The red part is moving back and forth horizontally. The imaginary part is moving back and forth vertically. And the thing is, if I change the sign of the frequency, if I now put a negative frequency, immediately I can see the difference on the complex number. It is rotating in the other direction. However, if I look only at the real part or only at the imaginary part, I cannot see whether the frequency is positive or negative. The only thing I see is something moving back and forth. So I hope this example really convinces you that positive and negative frequency is something that happens in complex numbers because they are 2D, two dimension. When we have a real signal, there's just one dimension and we cannot tell the difference between positive and negative frequencies. They are intrinsically the same thing. Any questions about this? Okay, final thing about IQ sampling or complex signals is maybe we have an input signal which is not complex. The previous week, we were seeing the RTL-SDR radio that we have. It's already giving us complex numbers because that's what everyone wants to do digital signal processing. But in some cases, for example, in the Allen telescope array, when we go there, I will mention how the ADCs, the analog to digital converters, which are used there, give us real signals. So there are some cases in which, for uh, different practical reasons, we might not have access to complex signals on the instrument we are using, and we only get real signals. So then the question is how to operate with those. And I'm going to do a third example by multiplying this one, by modifying this one, sorry, copying and pasting. Do I want this? No. And what I want to do is what happens if my signal is floating point like this. And I can try to shift it in frequency. I can multiply it by a cosine function as before. But in order to do that in GNU radio, I cannot directly multiply a real number and a complex number, even though mathematically that's something you can do. We need to convert. So I think there's no real to complex. I need to do the same thing as before. So I'm basically going to copy and paste these two blocks. So this is basically we are looking at the same signal. We have just changed the data type to complex by putting it on the real part of the complex number. And then we can do the same thing as before. And we have this signal, which is 1 kilohertz. There is nothing on the imaginary part because the signal is real. But now what happens if I set the local oscillator frequency to 1000? What we have is on the output, on the product, we have something at 0 hertz. So this is the signal we intended. But we also have something at plus 2 kilohertz. And the reason is because the spectrum of the original input signal is symmetric. It is the spectrum in blue. And we are shifting everything up by 1 kilohertz. Then this blue thing goes here. This blue thing goes there. And probably I should have put minus 1 kilohertz rather than plus 1 kilohertz, because that is the usual way of proceeding. We translate this one here, and if there was another signal which was slightly to the right of this, it will end slightly to the right of 0. And conversely, if there was something on the left, it ends up here. So that's the proper sideband. That is how they are called: positive sideband, negative sideband, that we want to translate to 0. If we had translated this one, then if we have something of less negative frequency, it's on the right, and now it has slightly positive frequency, so that's confusing. That's the reason to prefer translating this one. So yeah, it's almost the same thing as before. We get the signal we wanted here at 0 hertz, but we also get this additional signal that we need to get rid of by filtering. So that's how The RTL-SDR, for example, works when we tune to an FM radio station. Let's say it's at 95 megahertz. It is generating a local oscillator at 95 megahertz, which is complex. And you might tell me these are electrical signals. What's a complex electrical signal? It's actually two separate electrical signals going on different wires that are the real part and imaginary part of this complex signal. So you basically have the cosine and the sine generated as local oscillator. Both of them are multiplied with the real input signal because the input signal is the voltage at the antenna connector. That is a single real signal always. And we generate a real and imaginary part for the product. And those are the voltages on two different wires. We are doing this product of real number times a complex. It gives you two different real numbers or a complex number, and we convert them to digital numbers that go to the computer. This is how the RTL-SDR stick you have works. It's doing the same thing as this, but electronically rather than digitally. And there is a filter to remove this additional signal. So in the case of the FM radio station, if we are tuning to 95 megahertz, we would get the intended signal at 0 hertz or near 0 hertz. If there are some frequency errors, and we will get something at twice 95 megahertz or minus 2 times 95 megahertz, which is 190 megahertz. And there is a filter which removes all the high frequencies before converting to the digital domain. So that is one way of doing things. Basically, you translate things and then you remove this with a filter. The second way of doing this, and I'm going to show it just for completeness, is something which is called the Hilbert transform or Hilbert filter in digital signal processing. And that is something that has as input a real signal and gives you as output a complex signal. The real part of this complex signal is going to be the same thing as the input. The imaginary part is going to be basically whatever signal you need to have so as to remove all the negative frequencies. This is basically a filter which is removing all the negative frequencies on the input signal as well as it can, and it's never going to be perfect. I will show the example in a second. So it is a way of thinking that it is basically doing the same thing as converting from this real cosine to this complex cosine. If I give you a cosine function here in the real part, then give me the same cosine in the real part, but also give me the corresponding sine function. So that is the same cosine delayed by 90 degrees on the imaginary part. That is called the conjugate function of the input. So let's see how that works and if it does anything useful for us. We can see, let me just look at the input signal. So the thing I'm looking at is actually the output of this Hilbert filter. The input is a real signal. We know already too well how it has the same thing. But because this Hilbert filter it's basically trying to give me the sine function, which is in quadrature with this one. The amplitude is not quite right, and the reason for that is because this is a digital filter and it's never going to be perfect. And the closer we get to 0, the worse it's going to be. But even so, it's giving me something that it's already decreasing the amplitude of the negative frequency. If I keep increasing the frequency, you can see I go to 2 kilohertz. Now this almost has the same amplitude as the input signal, and the negative frequency has diminished in power more, and I can keep increasing this. So 3 kilohertz, almost the same, 4 kilohertz, basically the same. And now there is a very large difference in power. This is minus 9 dB. This is minus 65. So that difference is already large enough that this is absent for most practical purposes. So that is what a Hilbert filter does. It basically converts from real to complex by removing all the negative frequencies so that you only get the positive frequencies. And that is the same thing as finding an equivalent signal like this, which for this very simple input signal, it is just lagging things by 90 degrees. But if we have a more complicated waveform in the input, then the complementary imaginary signal might look much more different from the input signal. So for the second part of today, I'm going to be explaining how to do spectral analysis, as I mentioned at the beginning, and also how to generate some different types of signals. And we will also be speaking about signal to noise ratio, which is something essential if we want to know when we can detect a given signal, because a signal might be just too weak that it is statistically impossible for us to detect. And signal to noise ratio gives us a way of quantifying that. And whenever we speak of any kind of detection algorithm, and that detection algorithm might be for techno signatures, or it might be a radio communications receiver or something like that, we can speak of its sensitivity, which is the minimum signal to noise ratio can detect. For this part of the tutorial, I'm basically going to use the spectral analysis flow graph, which is, if you go to the GitHub RU 2025, spectral analysis GRC, because in the interest of time, I'm not going to put everything together. You can see there are multiple QTQE entries, etc., and it will take a bit of time to put all of that from scratch, but I'm going to start by disabling everything, and I will be explaining things as I keep building it. So I have something which is built, but I'm going to pretend that I built it from scratch, if that makes sense. So frequency sync. We want to look at the spectrum of signals. That is the whole point of this tutorial. And we know we can do that with the frequency sync. Parameters which are relevant, I'm using a sampling rate of 1 million samples per second. So that gives me 1 megahertz of spectrum. It is reasonable for a simulation. And the first thing I should let you know how to simulate is noise, because so far we have been generating signals with this signal source, which can generate some fairly simple deterministic signal types, such as a constant, trigonometric function, square wave, triangle wave, sawtooth wave. If you have used any kind of audio synthesizer, you are maybe you are familiar with this. But noise is random, and noise is present in any realistic radio frequency observation or simulation, because the instruments have noise, any kind of electronics has noise, and there are many noise sources. If we are looking at space, we have the cosmic microwave background. We have, depending on the frequency, noise sources coming from the galaxy, from the Milky Way. We have interference depending on where we have our receiver. Hopefully, it is a quiet zone if it's going to be a radio telescope, but even so, we have human-made interference. So all of that is noise, and the most simple type of noise is Gaussian noise. It's just a complex Gaussian random variable. You generate independent random Gaussian numbers for the real part and imaginary part with an amplitude, or maybe I should say standard deviation. And there is a small detail that this standard deviation is I should say this gives the power of the noise here. And power of a complex number, as you might know, is the modulus squared of the complex number, which is the same thing as the real part squared plus the imaginary part squared. And then what happens is basically the real part has half of the power, the imaginary part has half of the power. So the standard deviation on the real part, for example, is square root of 2 divided by 2. And the imaginary part is the same, so that when we compute the variance or when we compute the average power, we get 1. So that is what the amplitude stands for. It's in practice, it is more useful to think about the total power of the complex noise than to think about the standard deviation of the real part alone, for example. So that's the reason why it's defined in this way. So anyhow, for simplicity, I have a noise amplitude variable, but it's always going to be set to 1. And then since we are doing a simulation, I also have a throttle. And let's see how this looks like. It's going to be, as you can imagine, so it's white noise. That means it has the same power in all the frequencies, or the same average power. Because it is random, it only makes sense to speak about statistics like average power. So the average power where you can more or less see where it should be. There is an FFT averaging, which I already have set on medium. I can set it on high, and it helps a little bit. So this is noise, basically. You can see it's random, it's constantly changing, but it's flat, and it has a given average power. No surprises here. This is going to represent the noise floor of our receiver, and on top of this, or in combination with this, we will have some signals that we are interested in receiving or detecting. So for example, the simplest type of signal, we have already used this a couple times, is the signal source. Let's look at the parameters I have here. We have the sample rate, we have a frequency, this is the tone frequency here, 100 kilohertz. I have a formula of the amplitude. I will come back to this formula in a second. For the time being, it doesn't really matter. And then the rest of the parameters are set to the defaults of 0. So the results of this should be not very surprising. We have the noise floor here, and there is a signal in here. It is a narrowband signal. It is a single tone. This is usually called a CW carrier at a frequency of 0.1 megahertz, which is 100 kilohertz, which is what I have here, and I can change that. If I want, I can set 50 kilohertz, for example, and it jumps here. And you can see that it doesn't jump instantaneously because of the averaging. So if I remove the averaging, you can see it is much noisier, but then the jump is instantaneous. So there are advantages and disadvantages of using averaging here, as you can imagine. And then I have something called CN0 here, which I will explain in a second. This is used to set the signal to noise ratio of the signal. At the moment it is set as 60, and I'm going to decrease it. I'm going to set it at 50. This is in decibels. So it has gone down by 50 decibels, 40 goes down by 10 decibels more. Maybe let's put 20. It goes down by 20 decibels more, and maybe I should set this to 25. Okay, maybe 30. Okay, so with 30, I can see the signal. It is there. Sometimes it is stronger, other times it is weaker. That's because of the random noise, not because of the signal. The signal is always the same. So the variations are just the contribution of the noise. And my point is there is a minimum signal to noise ratio at which I can reliably detect this signal. It might be slightly less than 30 decibels, but if I go to 25, then I've lost the signal. Well, it appears sometimes, but maybe 22, it is completely gone. And I cannot see it anymore. I cannot see any difference here exactly at 100 kilohertz. So that is the sensitivity of the plot we have in here. Such a signal we can detect at 22 decibels, whatever this means. Um, any questions at this moment? I'm going to explain what the units are here, what sin zero means, how it is calculated, etc. in a second. Okay, so signal to noise ratio. The signal to noise ratio, as the name says, is a ratio, and ratio means the quotient, the division between two numbers of the signal power. And whenever we have something that we are calling signal because we are interested in it, let me get this back to 40 to be able to point at something. So the signal for us is this thing. It has a power, and we might be able to measure it, to estimate it, or to know it because this is a simulation, so I already know the power at which I have set the signal because it's given by the amplitude and by that formula that I'm going to explain. So that is what goes on the numerator of this fraction. The thing that goes on the denominator, signal to noise ratio. So it's noise, the power of the noise. But speaking about power of noise is slightly more tricky because it depends on how much bandwidth we use to measure the noise. Uh, Maybe you are already familiar that we can measure power in the spectrum. If I were to measure all the power that occurs, let's say within that piece of spectrum, the thing I want to do is to compute the integral of this, basically the area under the plot. Not in dB units, I would need to use linear power units, as they are called, so not decibel, linear units, but nevertheless, to compute power, I need to integrate all of this. So it's basically the integral of the frequency domain over the region that we are interested in measuring the power of. And then if we think about Gaussian noise like this, it is something that on average is flat. So it's going to be the integral of a constant over a certain bandwidth. And that means that the power of this noise floor is proportional to the bandwidth we measure it in. We could say it is the whole noise power that we are seeing here. So here I have 1 megahertz of noise because my bandwidth is 1 megahertz. You can see that it goes from minus 100 kilohertz, minus 500 kilohertz to plus 500 kilohertz because my sample rate is 1 megasample per second. And that would be a fine way to measure noise power. But then you need to remember when you are communicating this to another person or in some document, you need to say, I'm measuring the noise at 1 megahertz bandwidth because that person might have done manipulations with the signal. Maybe they have selected only this bandwidth and then 1 megahertz is no longer a number that is relevant for the problem. So you always need to keep saying, I'm measuring the noise in 1 megahertz or in whatever bandwidth you are measuring. And for that, there is a common bandwidth for measuring noise that many people use, and it is 1 hertz. And why 1 hertz? Well, because hertz is the unit of frequency, and 1 is the most simple number you can have. It is a tiny bandwidth to measure noise. So usually the way this is done is you measure noise in practice in a larger bandwidth. So you might measure the noise in all your 1 megahertz bandwidth if you need to measure experimentally. And then you say, well, my noise power is something, I don't know, 7, the number 7, whatever the units are. And then if I want to know the noise power in 1 hertz, I need to divide by 1 million because I'm doing 1 megahertz, which is 1 million hertz. And you do 7 divided by a million. And that is how you know what is your noise in 1 hertz. The notation for that is N0. So anytime you see N0, that's noise power in 1 hertz. And then CN0, that's what it means. C is carrier power, and carrier is basically another name for signal in most contexts. So it is the power of the signal divided by the power of the noise in 1 hertz. And we can write it in decibels or we cannot. It is commonly written in decibels. So that is what this means. So for example, 40 decibels means 10 to the power 4. That is 10,000. That means that this signal is 10,000 times more powerful than the noise in 1 hertz. Or in other way of speaking, the power of the signal is the same as the power of the noise in 10,000 hertz of noise. That's how you can think about this. In another way, you can look at 10,000 hertz of spectrum. I don't know how it would be. So for example, from here, from 110 to 120. So this small slice of noise has the same power as this CW signal here. So that is how we use the noise, the signal to noise ratio in decibels as CN0. How can we calculate things, or what is the formula of the amplitude for the signal to set it at the correct CN0? So it is this formula. So the CN0, we are setting it in decibels. We need to convert back to power, and you know dB is 10 to the power of something in decibels divided by 10. That is how decibels are defined. So this is just my CN0 in linear units. Then I'm multiplying by the noise power in 1 hertz, and this is another variable. I will show you the formula for that in a second. And this will be the power of my signal. But the thing GNU Radio is asking me for is not the power, but the amplitude. And the thing you always need to remember is power is amplitude squared. So if we know the power is this and we need the amplitude, we need to take the square root, which I'm doing using NumPy. And that is the formula. So what's this N0? How is this calculated? It is the thing I mentioned before. I have my noise amplitude. Okay, it is 1. I want my noise power, so noise amplitude squared. It is still 1, but I'm using it in the formula so that it is true in general. So this is my noise power across the whole bandwidth that I'm generating noise at. And in this case, that's 1 megahertz, and that's my sample rate. So which is 1 million. So the noise in 1 hertz is noise power divided by bandwidth in hertz, which is basically 1 divided by 1 million, which is this 10 to the power minus 6. This is 1 U is 1 micro something. That is how GNU Radio writes 10 to the power minus 6. So that is how the amplitude is set on the signal. And for example, the default I have 60, 60 is 10 to the power 6, which is a million. So even if it's hard to believe, the power of the signal, which is concentrated just here, is the same as the power of all this noise in 1 megahertz of spectrum. Questions at this moment? Okay, so we now know how to generate noise, how to generate a CW carrier or narrowband signal. And those kinds of signals are very important for SETI detection because many SETI detection algorithms work with narrowband signals, but there are also wideband signals. So let me show you how a wideband signal should look like before I tell you how we can generate it in GNU Radio. It will be more clear in this way. So now we see in this part of the spectrum, we have a signal which is 150 kilohertz wide. I have it here. So it's basically noise, but it has more power than the noise floor. It is meant to be another signal. This might be any kind of radio transmitter. and we can set its power to whatever we want. Not this one, sorry, the wideband CN0. So 80, for example, we make it larger. Many communication signals look like this. Some astronomical sources also look like this because ideally they would be like this, but there are Doppler effect or other factors that broaden the spectral line. If you have heard about spectral lines, an ideal spectral line is like this, but it can become broadened by a number of reasons. So these signals also show up in nature. How can we generate them in GNU radio? Well, an easy way is to start with noise. So since the thing we want to do is to generate noise, but only in a certain part of the spectrum, let's begin just by generating noise. And we know how to do that. This noise, the amplitude is the same formula as before to set the CN0, except I'm using a different variable. And then the next thing I need to do is to limit the noise to a certain bandwidth. And the easiest way of doing this in GNU Radio is slightly confusing if you haven't seen it before, because it is with this polyphase arbitrary resampler. And let me explain it in this way, what this is doing. So this is taking a signal which is noise within a certain bandwidth. And by resampling, we say we want to transform the sample rate to something else. For example, for what we have in here, the resampling rate is 6.666. So that means we want to increase the sample rate by a factor 6.666. Let's do other numbers so that it is simpler. Let me put 100 kilohertz in here. So I want to generate 100 kilohertz of noise, but then I want to put that into 1 megahertz of bandwidth. So now the resampling rate, which is my sample rate divided by the wideband bandwidth, is 10, basically 1 million divided by 10,000 kilohertz. So I want to convert this noise and to put it into something that has 10 times more bandwidth. And this resampler has a filter which basically tries to put 0 in the rest of the spectrum. So you can think of the original spectrum, you divide it. You can think of the resulting spectrum, you divide it into 10 different pieces because you are interpolating by a factor of 10. In one of those pieces, you put your original signal. In the rest, the remaining 9 pieces, you put zeros, basically. And that is how we accomplish this noise, which is flat. It basically occupies whatever, all the bandwidth, how we make it occupy only 100 kilohertz by using this polyphase arbitrary resampler. And if I do not use this multiplication block, let me do it like this, then it will be in the center of the spectrum. So basically we had something that was this as the noise source output, and we are putting this as the center of our complete spectrum. And this is 1/10 of the spectrum. The remaining 9/10 is zeros. Maybe it is even clearer if I only show this signal. So I remove all the rest. And this is the output. The resampler is not perfect. There are some numerical artifacts. But besides that, it basically tries to put the input signal in the 1/10 in the center of the spectrum and as close as 0 as it can get in the remains of the spectrum. So that's how it works, and that's how I can obtain a signal which looks like noise, but it has the bandwidth I want. And I can even change this number at runtime. The nice thing is this resampling rate can be changed at runtime. So for example, if I do 200 kilohertz, then the number here becomes 5, this at runtime, and this is now 200 kilohertz wide. So it's twice as wide. And I can keep playing with that, so 400 kilohertz, and it can be anything I want. So for using this in a nice way in our flow graph, we are multiplying it by a signal source in order to shift it in frequency. And this is an operation that we have seen in the first part of today's tutorial. So this is how I get something which is 100 kilohertz wide and centered at minus 300 kilohertz. And I can play the same game as before. I can decrease the power of the signal, maybe 30 decibels. And that's already too weak, I think. So 35 decibels. Maybe, I don't know. Maybe we can try the highest averaging. So maybe, just maybe, we are able to see something. 40, I don't think I see it. 45, yeah, at 45 we see a small thing in the spectrum. So that's about how weak of a signal with this particular bandwidth we can detect on this particular spectrum display. And any questions at this point about how to generate this wideband signal? Okay, so the next thing I want to do is to do a better spectrum display. Because to be honest with you, this one, which is the default frequency sync, is not very good. We can see that the noise floor is still moving, even though I have the average set to high. And yeah, that means that there are some weak signals we cannot detect with confidence. So we can do better by doing something like this, but by hand. And by doing so, we can also learn how this block works, because we are going to do something very similar but using multiple blocks. Something else I want to show is this virtual sink and virtual source. This is a way of connecting 2 points without running a direct connection. I could run a direct connection in this way, but then the flow graph is messier. So we can have this virtual sink and put a name in here, and then we have a virtual source. We put a name in here, and that is just like a direct connection from this one to this one. They are matched by name. So it is good to keep things nice and tidy. And the thing I'm going to do is an FFT. I've been mentioning the FFT, the Fourier transform. It converts from time domain, which is everything here is time domain, to frequency domain, which is what we want to display in the plot. So there is an FFT block for that. But the FFT operates on vectors, because an FFT is an operation that you do on blocks of data. That's what the FFT size means. It means that you take 4096 samples, or whatever the FFT size you decide, and you compute the FFT of those 4096 samples. Then you get the next 4096 samples, you compute the FFT of those, and then you keep going. So it works on blocks of 4096 samples. It doesn't make sense to give 5 samples to a block and say, hey, compute the FFT of this, because it needs to operate on blocks of 4096. And the way that GNU Radio does this, whenever you have something that needs to be blocks of an exact size, is with something that is called vectors. And that's the dark blue. If you look at the difference, this is light blue and this is dark blue. This is because these are vectors. So the FFT size wants to have an input which is a vector. If I try to do a direct connection, I get an error. And you can see in here the size 8, which is the size in bytes of a single complex number, does not match the size 32 blah 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 thousand bytes, which is the size of 4096 complex numbers. So we need to do something, and that something is to convert to a vector. This takes 4096 samples, which is defined by this NFFT variable. It's up here somewhere. I don't know where I've put it here. So NFFT 4096 samples. It is used in a few of these blocks since many of them need the vector size. So this one is using, it's getting NFFT, so 4096 elements, and it is putting them on a vector. Slightly confusingly, this is the vector length. This is actually the input vector length, which is 1, because here we don't have vectors in the input. So we are transforming from something which is not a vector really, so vector size 1, into vectors of size 4096, which is the thing that the FFT needs. What are the parameters on the FFT? Basically, I have them all at their default values except for the NFFT parameter, which I have at, well, FFT size 4096, as I mentioned. There's a window. I'm going to speak more about window at the end of today's tutorial. But this is the default, and it's usually a good default. The next thing we need to do is to obtain the power, because the FFT gives me complex numbers. It gives me power and phase at each frequency bin. The power of a complex number is the magnitude squared. It is real part squared plus imaginary part squared. And we can compute that with this, it's a math block. It's on, it's actually on type converters, so complex to magnitude squared. And this block also needs to know about the FFT size, because if I have it as 1, which is how it comes by default, it will complain about the connection type. So NFFT goes in here. And the next thing we want to do is to average, because by averaging, we reduce noise, we reduce data rate, and also we are plotting these on the screen. So to give you some numbers, the sample rate is 1 million samples per second originally. When we apply the FFT, we need 4096 of those samples to obtain each FFT vector. But basically here we have 25,000 FFTs per second, because that's 1 million divided by 4,000, I think. So we have 25,000 of these spectrum. Somehow the numbers don't seem right. Not 25,000, sorry. Actually 244. That is 1 million divided by 4096. However I put it, I will explain this formula in a second, but for the moment, bear with me. So regardless, 1 million divided by 4096 gives us something like 244. It doesn't make sense to plot 244 spectra per second on the screen, because the human eye is not even able to see 244 frames per second. So we want to integrate, to reduce noise, to reduce data rate to something which is reasonable for plotting on the screen at real time. And I'm using an integration time or an averaging time. It's usually called integration time in astronomy of 1 second. That means I'm going to add all the FFTs that are done in 1 second. And how many of those we have? So we have the sample rate divided by the number of samples in each FFT, so divided by 4096. And then we multiply by the integration time in seconds. In general, this will be a floating point number. We round it to get the nearest integer, because we can only integrate an integer number of FFTs. And this is what gives me 244. So I know there are 244 FFTs per second. And I'm adding all of them in this integrate block. So this integrate block is summing 244 FFTs and then producing a result. It's summing the next 244 FFTs, producing the next result, and so on. And again, we need to set the vector length. Then I need to convert to dBs, because this plot is in dBs, and sorry, I've somehow changed my tab in here. So this plot is in dBs, the frequency sync. And many times we want to plot spectrum in dBs unless we are dealing with very weak signals and we do not have any other strong signals. Because dBs are a way of plotting at the same time weak and strong signals and be able to see both of them. Otherwise, the weak signals would be like really, really tiny. So to convert to dBs, the formula is 10 times the logarithm 10 of the value. And that is done by putting 10 here, logarithm 10. If we go to the documentation, it says this computes 10 or n times the logarithm 10 of the input plus a number k in case you want to adjust things by moving them up and down by a constant. But we do not need it, so 10 times the logarithm. Again, vector length. What else? Repetition. This is a technical detail about GNU Radio. It doesn't have to do anything with signal processing. So what happens is I want to put this into this vector sync, which is a display plot. And ideally, I would be doing a direct connection, and this would be sending 1 spectrum per second, and this would be displaying 1 spectrum per second. But because of technical reasons, if I do that, then GNU Radio will not update the plot immediately. I can show this to you. So it's not updating anything in here. It takes a while because there are buffers in how GNU Radio works internally. And so we need to fill that this first buffer for us to be able to get any output. And now we have some output, but this is inconvenient. I was like speaking for 10 to 20 seconds without getting any output. And there is a simple way to get around this, which is we repeat. Every second, this is generating a measurement, but just for the purposes of forcing the plot to update faster, we repeat the same measurement 100 times. And that fills up the buffer. So the plot says, hey, I already have enough data to update myself. And it updates and maybe it overwrites itself 100 times with the same plot. It doesn't matter. We just want to have the plot fast. So now you can see it's fast. Every second, I'm getting a new plot. And we can zoom in here. And we can see it's the same thing as the Qt GUI plot. So this is the GNU Radio Qt GUI plot. This is the one we have built by hand with the FFT, the integrate and everything. This one is updating every second because we have set the integration time to 1 second. So it's computing with 1 second of data, putting it on the screen and repeating. This one is updating smoothly because it uses a different way of averaging. It doesn't work on blocks. It's doing a continuous averaging mechanism, which is known as a one pole IIR filter, if you are curious about it. But it's worse. It's in many cases, it's better to do integration by blocks as we are doing here. And then we get 1 second of data, and so the noise has reduced. Basically, the noise variance, as you can see here, is reduced proportionally to the integration length. Or another way of saying it, the signal to noise ratio we get on this, or how spiky or irregular this noise floor is, decreases with the square root of the integration length. So yeah, the square root is annoying because to get this twice better, we need to integrate 4 times more, but it is how it is. So let's actually test if this is any better than this plot, and I say it is, because for example, 35 decibels, I think we should still be able, well, maybe not, but maybe 37. Yeah, maybe 37 we can. We can, maybe with some luck, see that in this part of the spectrum, the signal is more powerful than in the other one. And And at 40, I'm already beginning to see, you can already see a hump, small hump in the spectrum here. 43 might be even clearer. You can clearly see it here. It's already starting to be visible there, but the fact that the noise is just more wavy in here doesn't help. And the same thing is true for this narrowband signal. So you can see 30, okay, can still see it in both. 25, here it's gone. It's there. If we know exactly what it is, we can try to see it, but there are other peaks which come up occasionally, which are not the signal. And in here you can see it's a small peak. I can zoom in. It's a small peak, but it's always there because the noise variance has been reduced by proper averaging the data through 1 second. So this is the proper way to construct a good spectrum analyzer, and we can detect Voyager with this one, with this technique. With Greenbank, it is easy. It's a 100-meter dish, so we do not even need to do this carefully. But we can also do with a smaller dish. We can do it with the Allen Telescope Array, for example, with a single 6-meter dish. It might take 15 minutes or even half an hour of integration for us to be able to see the signal. And we probably do not want to be staring at the plot for 15 minutes until it updates. So we want to record data and then do it in post-processing. But nevertheless, the technique is the same. Just integrate long enough, build up SNR, and then you will see the signal like this. For that, it's essential that the signal is always at the same frequency and that it is narrowband. So we need to correct for Doppler, and I will probably speak about that on another day. But for right now, you have this notion. Any questions? Okay, in the few minutes I have left, I want to speak a little bit about FFT windows and why they matter. What are some things to keep in mind when using FFTs? And I'm going to use this plot, but maybe not. Let me see. Yeah, can I put markers? Yes. So I'm going to use this plot, but any of them is good. So I know that my signal is a pure tone exactly at 100 kilohertz. So in the spectrum, I should see something right here and nothing else there. But even so, if I look at these closely by putting dots in all the FFT beams, I see that my signal is in all of these. And also my signal is halfway between the FFT beams because they do not line exactly with the signal frequency. I can play a little bit with this frequency. Let me try to see if I get it right. So now with 100 kilohertz point one, the signal is almost exactly in one of the FFT beams. You can see these two are the same height. So this is how I know the signal is well centered. And you can see that there is also a small difference in power. I'm going to, can I do max hold on this one? I don't think I can, but I can look at the level. So this is 87 decibels. If I put this back to where it was, where it's almost halfway, and I'm actually going to put it at maybe, let me do it, I think 0.22. This is exactly halfway. So I've moved it so that it is exactly halfway, and it is slightly less amplitude. And that makes sense because when the FFT beam lines up exactly with the signal frequency, then the signal falls exactly on top of the thing we are measuring with the FFT, and we get all the power of the signal there. When the signal falls in between two FFT beams, somehow the power is divided between two adjacent FFT beams, and so we have a small reduction in the power we see. That is called scalloping losses. So whenever you see spectrum of a signal and you say, hey, my signal is something I see on the spectrum. That might not be completely right because depending on how the signal, if it's an narrowband signal like this, depending on how the signal is aligned with the FFT beams, it might have some scalloping losses, as in this example. So this is one of the things that the FFT window can help us with. Depending on the depending on the window we choose, we will have more or less scalloping losses. And there are actually some FFT windows which have zero scalloping losses. So if you want to measure power very accurately without having to rely on whether the signal falls on top of one of the FFT bins exactly or halfway between bins, we would use one of those bins, one of those windows, which are called flat top windows, because they have no scalloping losses. So that's something that the FFT bins, the FFT windows, sorry, are useful for. The other one is the leakage. So basically my signal is here, but I also see some signal power in there. That is because of the FFT leakage. It's not possible to design an FFT window so that the signal appears only in these two bins or only in one bin where it's perfectly, when it's perfectly lined up. Well, when it's exactly perfectly lined up, there is a way to have a window which only shows the signal here, and I will show you how in a second. But if the signal is not exactly lined up with the FFT bins, it's impossible. It's like designing an ideal filter. It's impossible. So we have to do with one way or another have some leakage in the shape of this signal, and that is also determined by the uh, FFT window. And there are windows which have wider leakage, and there are windows with narrower leakage. And usually we cannot optimize for both scalloping losses and for this leakage. If we choose to optimize one of them, we lose on the other one. That's how these problems usually behave. So this is with the default window, which is the Blackman-Harris window. It's a usual window. It is good in all respects. So unless you you really need like a very specific window for a very specific reason, like the flat top window I mentioned, you can stick with Blackman-Harris. I'm going to show you the rectangular window, which is like no window. It's just a bunch of ones. So that's performing the FFT without applying any window. And then the thing we can see is, well, leakage is horrible. So that's the reason. Sorry, I want to put in here, where is the marker? So you can see, yeah, many points. Before it was only 4 or 5 on each side, but now we have this curve, which is horrible. You can imagine if we had a small signal right in here, it would be completely hidden by my skirt from this one. So this is the reason that the rectangular window is not commonly used in practice. However, there's something good about it besides performance. For performance, it's good because any other window means you need to multiply by the window. In this one, since the window is ones, you do not need to multiply by anything. But the other nice thing is that if I manage to get my frequency exactly aligned with the FFT, then you can see that suddenly it has no skirt. It doesn't have any leakage. And that's because of how the FFT works. Um, the FFT with no window, if you throw in exactly the frequency of one of the FFT bins, you only get something in that particular FFT bins and zeros the rest. Here I'm getting the noise, but because I have some noise floor, but mathematically with just the input signal, I would get zeros everywhere else. So that's the nice thing about the rectangular window. Regarding scalloping loss, it's particularly bad, but it is also simple to figure out how it works. It basically gives you half of the power in the two adjacent bins. So we can see this is 96.6. If I set 0.22, 92 point something. And I would expect this difference to be about 3 decibels. It's probably not exactly 3 decibels because we also have some leakage here, but basically that's what we get. The total power needs to be the same. That's also another nice thing about the rectangular window, regardless of how the signal is aligned with the FFT beams. If you sum all the power, so here that involves all this curve, we should get the same as when the signal was concentrated in a single FFT beam. So that is the deal about FFT windows and why they exist, why you might want to choose one instead of the other one. And that is basically all I had today. Any questions about Windows or anything else we